So we are on page 189, the zeros of polynomial functions, okay? So the zeros, so zeros meaning solutions, right? Meaning x-intercepts, which also the same thing as root, right? They're all solutions, right? So let's see if we can do example number 5. Find the zeros of x cubed minus x squared minus 6x. Okay, so if I'm going to do this algebraically, since I don't have a constant term, everything has an x, so I can go ahead and pull the x out. I'm going to end up with x squared minus x minus 6. So now I have to factor this. So this factors out in negative 3 and 2, right? X negative 3 and plus 2. Okay, so that's that. So it's equal to 0, which means that this guy can be 0, or this guy can be 0, or this guy is 0, right? So x can be 0, or x minus 3 can be 0, or x plus 2 can be 0. So I move this over, I get x is equal to 3. If I move this guy over, x is equal to negative 2. So I have 1, 2, 3 answers, right? Okay, so that's how you would do that. Okay. Now, sometimes you're going to end up with things that look like, so I'm going to have 3. So if I go ahead and graph this, what am I going to look like? I'm going to look like this, right? I'm going to have 0. So I'm going to have a 0 here and a 0 at 3 and a 0 at negative 2. And since it's x cubed and it's a positive, I'm going to start from here. It's going to look like this, right? 3, 0, and negative 2, right? So this is what it's going to look like, okay? But sometimes you're going to end up with things that look like this, right? Sometimes you're going to end up with things that look like x minus 1, x minus 2 squared, right? So again, this is a x to the third power, right? Because this is going to be x to the squared power. I'm going to have an x here, it's going to be x to the third, right? But where are my zeros here? I'm going to have a 0 at here. This could be 0. So it could be x equal to 1, or this could be 0, so x could be equal to 2. However, if you see here, I have a 2 here, right? So basically, I'm having 2 of the zeros that merge together here, right? So basically, what it's going to look like is this. I'm going to go like this. I'm going to merge together here, and like this, 1 and 2, right? So you have a 0 here and a 0 here. Now obviously, these two zeros are different, right? This one is, where this one actually goes through it. This one kind of just dips there, touches, and comes back up, right? It bounces back up, right? Okay. So these type of things we call a multiplicity. This is called a multiplicity. So here, when you end up with something like this is called a multiplicity. So this would be a multiplicity of 2. I can end up with multiplicity of 3, 4, 5, however it may be, right? Okay. So let's say that I had a, so let's say, let's look at this guy, f of x equal to x cubed. Okay. So actually this looks like this. We already know what this looks like, right? It looks like this and then 0, right? I only have one root here, but I have a multiplicity of 3. Now this multiplicity is different because in the multiplicity of 2, it went here and it kind of bounced back up and never went down, when it never went down here. But in an odd number multiplicity, I can go and it's going to go travel through the 0. Okay.
Mr. On.
So if you have even number multiplicity, it does not travel through, it goes here and it bounces back up. If you have an odd number multiplicity, then it comes here and it actually penetrates through and it goes down.
Mr. On.
Yes.
Allison got kicked out, so she's trying to get back in.
Okay. She hasn't gotten to the waiting room yet, but I'll take care of her once she gets to the waiting room. Thank you for letting me know. Okay. So on the bottom of page 189, read the multiplicity stuff there for me and see if that makes sense to you. Okay, so let's go ahead and go to page 190. And on page 190, there's another one of zeros of odd and even multiplicity, and it talks about whether it actually penetrates through the x-axis or not. So let's look at example number 6. Example number 6, state the degree and list the zeros of a function that, state the multiplicity, 0, where the graph crosses through or corresponds, and sketch the graph by hand. So I'm going to have f of x. This is example number 6. F of x is equal to x plus 2 cubed and x minus 1 squared. Okay, so this is a polynomial with a degree of 5, right? Because you're going x to the 5th is going to be your greatest one. Okay, now I have a multiplicity of 3 at -2. I have a multiplicity of 2 at x equal to 1. Okay, so let's see if I can draw this. Now I'm going to have at 1, I'm going to have -2 here. Okay, since it's a positive, the leading coefficient is positive, right? Because this is going to be x to the 5th something, whatever, right? So I'm going to have a lead, so it's going to be positive here. At x minus 1, I have a multiplicity of 2, which means that it's going to go like this, but it's not going to go through, right? So I'm going to start here, go like this, and go like this. It's going to come through here. Now here, it's an odd number multiplicity, so it's actually going to penetrate through 0. So it'll look like that. Okay, and I start from here, and I end up down there, which I should, because it's an odd number polynomial. It's a positive, so it starts here and go down there, right? Like that. If I gave you something that looked like this, and I have a minus here, if I had a minus here, then it was going to go down here, it would be the exact reflection, right? It would look like that. Okay, if I had the minus here, right? If I did. Okay, all right. Okay, so that's that. Okay, then in the middle of page 190, there is a thing called the intermediate value theorem. Intermediate value theorem, sometimes known as the IVT, intermediate value theorem. Okay, intermediate value theorem says, okay, if A and B are real numbers with A being less than B, and if F is continuous on the interval A to B, okay, in other words, if I have a function that looks like this is A, this is B, and this is function is f of x, this point here is going to be what? This point here is going to be f of A, right? Because it is basically the value of when I put A in here, right? for this. Okay, so over here, this value is going to be f of b. Okay, what it's saying is the IVT, the intermediate value theorem, says that if the function is continuous between a and b, then the value of the function has to take on every value between f of a and f of b. Okay, it has to be, so you're going to take all the values of y between f of a and f of b. And that's what it says. Okay, so why is this important? Why is this important? It's important when you're going to go ahead and start stating things about solutions or roots, right? So if I had a function that looks like this, okay, and I find that if I call this a, and I call this guy b, okay, by the IVT, by the intermediate value theorem, right? Y has to take on all values between whatever this negative value all the way through the positive value here. So in order to take, if you take on all values, there has to be somewhere in here between A and B, the 0 has to be there. So there's a solution between A and B is what that means. Okay? So let's see. Okay, example number 7. Let's see if we do example number 7. Okay, explain why a polynomial function of odd degree has at least one 0. Okay, so if I have an odd number polynomial, I'm going to start here, right? If it's positive, if a out of n is positive, I start here and I have to go down here, right? So I know that the limit of when x is goes to infinity, f of x is equal to positive infinity, and the limit as x goes to negative infinity, f of x is going to negative infinity. So I know that somewhere in between here, to go between negative infinity and positive infinity, there has to be at least one 0. Okay, and that's due to the intermediate value theorem, right? Okay. Well, how does this work if this is a even number function? If it's an even number polynomial, I start here, I end up here, right? I can actually have a polynomial that looks like that. How many zeros do I have? None, right? None of them are going to go through this value. None of them meet the x-axis, which means that there are no solutions to this. Okay? So a very simple example of this would be y is equal to x squared plus 2. All right? Y is equal to x squared plus 2. The graph looks like this. It's never going to meet the x-axis, right? Okay, so there's no solutions there, right? Example number 8, find all of the real zeros of that function. And we're going to do this graphically, so you would just go ahead and graph it and you would look at it, okay? Now, the thing that they want you to see here is that if you see A, you graph, you look at the graph A, you might be inclined to say that there's only 2 solutions there, okay? But if you look really closely, there's going to be a little dip there where there are 2 roots that are fairly close to each other that might appear to be the same, okay? So always be careful to take a look at that to make sure that there are nothing like that happening. Okay, and we have the one modeling question, and here we go back to the book's very favorite designing a box question. Okay, so we're gonna do a 20 by 25 piece of the cardboard. So 20 by 25, and we are cutting out x by x squares here, folding them up to make it a open top box. Okay, so, and what are we trying to find? What size square should be cut from the cardboard to get a 484-inch cubed one? Okay, so the volume, okay, as we did before, we're gonna go ahead and flip these up like that. So the height is x, the height of the box is x, okay. This guy here is going to be 25 minus 2x because I'm cutting off x here and x here. And then this guy here is going to be 20 minus 2x. So again, I'm going to cut off x here and cut off x here. I'm cutting off two x's, right? So the volume is going to look like this. Okay. And the question is, when does this equal to 484, right? I want this to be equal to 484. Okay. So that's that. You just go ahead and graph it, right? So how would you graph this? I mean, you can go ahead and do this and say, where does that meet when it's 484? And I can go ahead and graph this and trace it to see where it reaches 484. Or I can go ahead and plot this guy, because I'm going to move this over on that side, and I'm going to see when this guy goes to 0, when it meets 0, right? So I can do that one too, either way. Okay. I would prefer this method because it's easier to find, see where the zeros are at. Okay. So that's that, we're good, and we are done. We are done with 2.3, okay? So let's go ahead